The cold blob near Greenland is doing the one thing scientists warned about years ago, and now that it is actually happening, researchers are describing the situation in genuinely alarming terms. For decades, this strange, stubborn patch of unusually cold water sitting in the North Atlantic has been treated as a curiosity, an anomaly that stood out simply because it kept cooling while the rest of the world's oceans grew warmer around it. New research has now confirmed the exact mechanism scientists long feared was driving that cooling, and the evidence points directly toward a weakening of one of the most important ocean current systems on the entire planet. To understand why this development is so unsettling, you first need to understand exactly what scientists have been watching for. The Atlantic Meridional Overturning Circulation, known as the AMOC, functions like an enormous conveyor belt running through the Atlantic Ocean, carrying warm tropical water northward toward Greenland and Iceland, where it eventually cools, becomes denser, and sinks before flowing back southward to complete an endless cycle. In its middle stretch, this system is more commonly known as the Gulf Stream, the very same current responsible for keeping much of Western Europe noticeably milder than other regions, sitting at comparable latitudes elsewhere around the globe. The cold blob sits precisely at the northern terminus of this vast circulation system, the exact spot where the AMOC delivers the bulk of its transported heat, which is why scientists have long treated unusual cooling in this specific location as a potential early warning sign rather than a simple regional oddity. For years, two competing explanations existed for why this patch kept defying the broader global warming trend surrounding it. One theory held that local atmospheric conditions, shifting winds, or persistent cloud cover were simply pulling more heat away from the ocean surface in that particular spot. The other, considerably more concerning theory suggested the AMOC itself was slowing down, delivering measurably less warm water into the region in the first place. New research published in geophysical research letters has now delivered some of the strongest evidence yet supporting that second, more troubling explanation, and it is exactly the outcome scientists had long warned represented the more dangerous possibility. Researchers led by Stefan Rahmstorf, an oceanologist at the Potsdam Institute for Climate Impact Research in Germany, combined direct temperature observations gathered from ocean instruments and satellites spanning nearly 70 years with detailed climate modeling, and the results were striking. The cooling extends far deeper than any surface-level atmospheric effect could possibly explain, reaching depths of up to 1,000 meters below the ocean surface. Since wind and cloud cover can only meaningfully influence temperatures near the immediate surface, finding substantial cooling at such extraordinary depth provides compelling evidence that the AMOC is genuinely transporting less warm water into this region overall, precisely the mechanism scientists had feared all along rather than a more benign, atmospherically driven explanation. If you're finding this breakdown genuinely important, take a moment to like this video and subscribe, because understanding exactly why researchers are treating this confirmation as such a serious development requires looking closely at what happens when an ocean system this significant continues losing strength. The underlying driver behind this weakening traces back to a feedback loop scientists have documented developing over recent decades, tied directly to accelerating ice loss. Human-driven warming has caused ice sheets and glaciers, particularly across Greenland, to melt at an increasing rate, sending a growing surge of cold, fresh water directly into the exact region where the AMOC depends on sufficiently salty, dense water sinking to keep its broader circulation moving. That influx of fresh water dilutes the salinity balance the entire system relies on, slowing the sinking process that drives the whole conveyor belt forward. As that slowdown continues, the AMOC loses momentum in a self-reinforcing cycle, one that helps explain why researchers describe the cold blob as actively growing rather than stabilizing or shrinking back toward its historical baseline size. What makes this confirmation feel especially significant to the scientists studying it is the specific language now appearing in the published research itself. The study's authors describe identifying what they call early warning signals, indicating the ocean circulation is approaching a genuine tipping point, a threshold beyond which continued weakening could become effectively irreversible regardless of any future changes in global emissions. The researchers state directly that this evidence represents a serious concern for society, requiring urgent attention from policymakers. Language considerably more direct than the cautious, heavily qualified tone typically found throughout most academic climate research, and a clear signal of just how seriously this particular research team views the confirmation they have uncovered. Understanding what a full AMOC collapse would ultimately mean helps explain why even gradual ongoing weakening generates this level of scientific concern. A complete shutdown of the system would represent a genuine global-scale catastrophe, according to researchers studying the broader consequences. Sea levels along the United States East Coast would rise considerably faster than the global average, since the current normally helps pull water away from that specific coastline as part of its regular circulation pattern, and losing that effect would allow water to pile up along the coastline instead. Beyond direct sea level impacts, a full collapse would plunge large portions of northern Europe into significantly colder average conditions, potentially disrupting monsoon patterns across parts of Africa severely enough to drive prolonged, devastating droughts, while simultaneously throwing broader tropical rainfall patterns into chaos with direct, serious consequences for agricultural production across multiple continents at once. Historical precedent for how this system has behaved during past disruptions offers a genuinely sobering perspective on just how long any recovery might take. Roughly 12,500 years ago, during an ancient cold period known as the Younger Dryas, the AMOC underwent a dramatic disruption of its own. Researchers studying that historical event found it took approximately 100 years for the circulation to become fully functional again, once conditions began improving, while temperatures in Greenland specifically needed around 40 years just to recover from the extreme glacial conditions that period produced. That timeline matters enormously for how today's scientists think about the currently weakening AMOC, since it demonstrates that meaningful disruption to this system, once genuinely triggered, does not simply reverse quickly even after the underlying causes begin easing, a possibility that would leave multiple generations dealing with the consequences of changes set in motion decades or centuries earlier. It's worth noting that not every researcher in this field agrees on how urgently the current findings should be interpreted, and legitimate scientific debate continues around exactly how close the AMOC actually sits to a genuine tipping point today. Some scientists examining this same body of evidence maintain that the underlying circulation remains fundamentally more stable than the most alarming interpretations suggest, arguing that a rapid, imminent collapse remains unlikely without truly extraordinary additional conditions developing well beyond what current data currently demonstrates. That disagreement reflects a broader and entirely normal pattern within climate science, where new evidence pointing toward a concerning trend does not automatically resolve every remaining uncertainty about exact timing, precise thresholds, or the full range of mechanisms potentially involved, meaning careful researchers continue treating this evolving picture with appropriate caution, even while taking the newly confirmed signal seriously. The practical, near-term implications of this weakening also carry a genuinely counterintuitive twist that researchers are working hard to communicate clearly. According to Dr. Dafydd Gwyn Evans, a senior research scientist in physical oceanography at the National Oceanography Center, the shorter-term effect of a persistent, growing cold blob has actually been linked to an increased likelihood of more extreme summer heat waves across the United Kingdom specifically, rather than the immediate cold snap its ominous nickname might suggest. Evans, who has co-authored research directly connecting cooling in this exact region to extreme European heat events, explains that the underlying mechanism comes down to how ocean temperature gradients influence the position of the jet stream, the high altitude current of wind that determines how far north or south weather systems tend to travel across the continent. As the temperature contrast between the cold blob and the surrounding warmer ocean water intensifies, it shifts the jet stream's typical path in ways that have historically correlated with more frequent and more intense summer heat events across Britain and its neighboring regions, even as the same underlying weakening carries the potential for measurably colder conditions across northern Europe over a longer, multi-decade time frame. Beyond the direct temperature and sea level consequences already outlined, a weakening AMOC carries meaningful implications for Atlantic storm behavior as well, adding yet another layer of risk to an already serious picture. Researchers studying the system note that continued weakening toward eventual collapse would likely increase overall storm intensity across the Atlantic basin, since the disruption to normal heat distribution patterns that drives the broader temperature effects also interacts directly with the atmospheric conditions that fuel storm development and strengthening. This means the consequences of a weakening AMOC extend well beyond simply making certain regions colder or warmer, reaching into the fundamental dynamics that determine how dangerous individual storm systems become once they form over the warm and increasingly disrupted waters of the Atlantic. Agricultural and economic planners across the regions most likely to feel these effects have already started incorporating this evolving research into longer-term risk assessments, even amid the remaining scientific uncertainty. European agricultural organizations, dependent on relatively stable seasonal temperature and rainfall patterns, face particular exposure, since a significantly weakened AMOC could disrupt growing seasons in ways that established farming practices, developed and refined over generations of comparatively stable climate conditions, may not adequately account for. Coastal communities along the United States East Coast face their own distinct set of long-term planning challenges, since accelerated sea level rise tied to AMOC weakening compounds, an already serious flooding risk that many coastal infrastructure systems were never originally designed to handle at this scale. The scientific and public discourse surrounding this research has also grown somewhat contentious in recent months, with some commentators pushing back against what they characterize as overly dramatic framing of the cold blob's broader significance. Critics point to previous instances where concerns about ocean circulation collapse were raised prominently and then significantly walked back as additional data emerged, arguing that the current wave of attention risks overstating the level of scientific certainty that actually exists around this genuinely complex and still evolving area of research. Scientists on the other side of that particular debate counter that the newer evidence, especially the deep water temperature findings extending well below the surface where atmospheric influence becomes negligible, represents meaningfully stronger proof than earlier, more preliminary studies could offer, since it directly rules out simpler atmospheric explanations that could previously have accounted for the observed surface-level cooling on their own. For people trying to gauge how seriously to take this particular finding amid that ongoing scientific disagreement, the most reasonable conclusion avoids both dismissing the concern entirely and treating an imminent near-term collapse as an already settled certainty. The underlying physical evidence supporting AMOC weakening has grown considerably stronger through this latest research, and the potential consequences of continued weakening remain serious enough that researchers across the broader field generally agree the situation warrants sustained close monitoring alongside genuine policy attention going forward. At the same time, meaningful uncertainty still surrounds the precise timeline over which any further weakening might unfold, meaning specific predictions about exactly how quickly conditions might deteriorate remain considerably harder to pin down with confidence than the broader underlying trend itself. Is that scientists are no longer debating whether something unusual is happening in this specific patch of ocean, but are instead confirming the precise mechanism driving it, and that mechanism happens to be exactly the one researchers had spent years warning could eventually prove most serious, combined with historical evidence showing just how long recovery from a major disruption to this system has taken in the past, and consequences that researchers describe in genuinely global civilization scale terms. It becomes considerably easier to understand why this particular research finding is generating such serious attention within the scientific community. If this breakdown of exactly why a cooling patch of Atlantic Ocean water has scientists so genuinely concerned helped clarify the real stakes behind this story, make sure you are subscribed, because researchers are continuing to monitor this evolving situation closely, and there is likely much more to learn as this research continues developing in the months ahead.